Good morning and welcome to this next lecture on vibrations of plates and shells. We have been looking at the Rayleigh Ritz method and we are now into two-dimensional structures like plates and shells, and we were deriving the Vm and the psi m terms for the most general case of a thin plate or shell, okay, and this is where we left off. Okay. Now in the paper that I mentioned, in this particular paper that I mentioned, okay, there is a non-dimensionalization the author does, which is here. It takes alpha as a by b, the ratio of the lengths, say xi as x over a and eta as y over b, which means del x is equal to del xi del x, which is 1 over a del xi. Okay. Similarly, del 2 del x square is equal to 1 over a square del 2 del xi square, and for the same reason del 2 del y square 1 over b square del 2 del eta square. Okay. So, if we implement this here, what do we get? We get V max as 1/2 integral 0 to 1 E h cube, this term I will put it as a d, then 1 over a fourth w xi squared plus 1 over b fourth w eta squared, okay, which is mean double derivative with respect to eta, plus twice mu by a square b square w xi w eta plus twice 1 minus mu by a square b square w square xi eta a b d xi d eta. Okay. So, that is equal to 1/2 integral 0 to 1 dAb by a fourth, divide by a fourth outside, multiply by a fourth inside. So, I get w xi squared plus alpha fourth, okay, alpha fourth w eta squared plus twice mu alpha squared w xi w eta plus twice 1 minus mu alpha squared w squared xi eta. Okay. Into d xi d eta, and psi m is a b rho h by 2 0 to 1 w square d xi d eta. So, if you implement this, what happens in the numerator and denominator, we have omega square, the Rayleigh quotient of the numerator has d AB by a fourth, the denominator we have AB rho h by 2. So, if I cancel AB, I get and sorry, there is a half here also. So, if I take out this 2 and that 2, I get d by a fourth rho h and the ratio of the remaining terms. Okay. So, let us call this lambda. Then lambda becomes equal to rho h omega square a fourth by a d, and what is listed is lambda, root of lambda. Okay. So, if you first find the omega square using the Rayleigh Ritz method, okay, that means what, del Vm by del Gi etc. Okay, and then del psi m by del Gi, if you do this method, okay, and finally get your omega squared, then the form of the frequency term presented in the paper is you multiply this omega square by rho h divided by d and multiply by a fourth and take a square root. That is what is listed in the paper. Okay. So, now what about the actual functions? Okay. In the earlier places for the cantilever beam, what did we see? We saw x by L whole squared, x by L whole cube, etc. So, here the author takes first. So, let me do one more thing, okay, in keeping with the paper, so that students do not get confused. I will switch back to xi as x and eta as y. So, x and y are the non-dimensionalized variables, that is how the author uses it. So, I will go back there. Okay. So, what are the functions? The function is in the x direction, I choose a 0 plus a1x plus a2x square plus a3 x cube plus a4 x fourth. Okay. Then my x dash is a1 plus twice a2x plus 3 a3x square plus 4 a4 x cube, and x double dash is twice a2 plus 6 a3x plus 12 a4x square. Okay. Now, if my plate is like this is x, that is y, then at the edges of the x Okay, let us say I am going to take a simply subordinate plate. Okay, that means what? X at 0 must be 0, okay, which means A0 is equal to 0, okay, and X double dash at 0 is 0, which means A2 is 0. Okay, that means what now? A0 is 0 and A2 is 0. So my X of X is equal to A1X plus A3X cube plus A4X cube. Okay. Further, X at 1 is equal to 0 also. Okay. Now X, I said X and Y are non-dimensionalized variables. So X1 is 0. If X1 is 0, that means A1 plus A3 plus A4 is 0. Okay. Further, if X double dash at 1 equal to 0, okay, then I have twice A2 plus 3A3. I am sorry, just hold on. A2 is 0 anyway, okay. So I have 6A3 plus 12A4 equal to 0, which means A3 is equal to minus 2A4. It's not writing here. A3 is equal to minus 2A4. Okay. So if I bring that into this, I get A1 is equal to A4. Okay. So what does that give me? My X of X is equal to A1X plus A3X cube plus A4X fourth, and A1 is equal to A4th. Okay. So I get A1X minus 2A1X cube plus A1X fourth, or A1 comes outside, X minus 2X cube plus X fourth. Okay. So I will choose the first one, phi 0, okay, of X as X minus 2X cube plus X fourth divided by integral 0 to 1, okay, X minus 2X cube plus X fourth squared and square root. Okay, which is just as if I say that my new function X of X is just X minus 2X cube plus X fourth without that arbitrary constant. This is X of X by integral 0 to 1 x square of x dx, okay, and half. That is phi 0, the first one in the x direction. Okay. So, how to find the others? How to find the others? So, you can see that first of all from here you can see that integral 0 to 1 phi 0 square of x dx is equal to integral 0 to 1 x square of x dx by this square root into the same thing's square root, which is equal to 1. Okay. So, now how to find the others? The way to find the others is phi 1 of x is x times phi 0 of x. This is another function, okay. But in order to make it orthogonal to phi 0, so this is the Gram-Schmidt orthonormalization. In order to find the one without phi 0, what I do is I subtract from here integral 0 to 1 x phi 0 of x and the component of phi 0 of x in it dx. Okay. And I divide by into phi 0 of x, into phi 0 of x. No need to divide anything, into phi 0 of x. Okay. Now, how do we know this is orthogonal to? Is phi 1 of x now orthogonal to phi 0? How do we know? How do we know that? Because now if I multiply phi 1 of x by phi 0 of x and integrate 0 to 1, I will do that here. What do I do? Multiply this by phi 0. So, that means on the right I get x phi 0 square, then I integrate from 0 to 1 dx. I have this term also, but this is already an integral, so I have this term. So, minus integral 0 to 1 this term x phi 0 square dx into, this is function of x. So, I have integral 0 to 1 just as I multiplied by phi 0, this is phi 0 square x dx. Okay. I just multiplied this equation by 1 phi 0 of x dx and integrated. That is all I did. So, what happens? This is already 1. Okay. So, what do I have? X phi 0 square dx, x phi 0 square dx with a minus. So, this is 0. That means what? Phi 1 and phi 0 are orthogonal. Okay. Now, I normalize phi 1 also. So, the phi 1 of x is going to be phi 1 of x divided by whatever you found, phi 1 square of x dx and square rooted. This is the new phi 1. This is the new phi 1. Okay. So, then how do you find next? How to find phi 2? we find phi 2 by saying, we change the pen here. Phi 2, I am sorry, phi 2. Phi 2 is now x times phi 1, okay. But I have to take out from here the component of phi 1 in it and phi 0 in it separately. So, minus integral 0 to 1 component of phi 1 in it is multiplied by phi 1 dx into phi 1. This much component of phi 1 is taken out from this, removed, okay. Then I remove integral 0 to 1 x phi 1 and the component of phi 0 in it. This is the dot product in terms of function, okay, dx, and that much component of phi 0 is taken out, okay. From x phi 1 I am taking out a certain part of phi 1 and a certain part of phi 0. What is that part? That part here is this. What is this part? This part here is this, okay. Then this is free of a component of phi 1, this is free of the component of phi 0, and therefore it is orthogonal, okay. So, now how do we know this is orthogonal to phi 0? Phi 0 orthogonal to phi 1 and phi 0. How do we know that? So, we will check it out, okay. So, we will check it out. So, we multiply phi 2 by phi 0, phi 2 by phi 0 and integrate and check, okay. So, if we do that, so that means basically this whole thing I multiply by phi 0 and integrate, okay. So, how do we do that? So, if I do that, on the left I have integral 0 to 1 phi 2 phi 0 dx. On the right I have x phi 1. So, multiply by phi 0, integrate 0 to 1 dx, and I have minus integral 0 to 1 x phi 1 square dx already, and I had phi 1. So, I have integral 0 to 1 phi 1 and phi 0 as I did here and here dx, and lastly I have minus integral 0 to 1 x phi 1 phi 0 dx already into phi 0. So, then I am multiply by one more phi 0, so phi 0 square dx, okay. Now, this is equal to 1 from orthonormalization, this is equal to 0. Earlier we proved phi 1 and phi 0 are orthogonal, okay. So, this is not there, okay. Now, I have x phi 1 phi 0 here minus x phi 1 phi 0 here, sorry, okay. This was 0. So, I have x phi 1 phi 0, x phi 1 phi 0 with a minus sign. So, this is 0. So, this is equal to 0. So, phi 2 is orthogonal to phi 0, okay. Now, we can check phi 2 phi 1, okay. Let us do that. So, integral 0 to 1 phi 2 into phi 1 dx is equal to, on the right side, integral x phi 1 into phi 1 0 to 1 I have minus integral 0 to 1 x phi 1 square dx already, and I have phi 1, so this is 0 to 1 phi 1 square dx, and this is 1 from orthonormalization, then minus integral 0 to 1 x phi 1 phi 0 dx, and I have phi 0, so I have 0 to 1 phi 0 into phi 1 dx. Now phi 0 phi 1 are orthogonal, so this goes to 0, so this term goes to 0. Now what do I have left? I have x phi 1 square and x phi 1 square with a minus, so this term is 0. So phi 2 and phi 1 are 0. So similarly we continue. We continue. Okay, find the higher order fellows. Okay. Now what next? What is the next step? So we have found something in the x direction, right? X direction. Okay, simply support it and say simply support it. Okay, then suppose I find in the y direction, I also find, so these are called, let us say x direction fellows are called phi's, y direction fellows are called chi's. Okay, so the y also I found a function that are simply supported. Okay, 1, 2, 3, chi 1, chi 2, chi 3, etc. Okay, so suppose I have found phi 0x, phi 1x, and phi 2 of x, and then in chi I found chi 0y, chi 1y, and chi 3y. Now what do? I have to represent the displacement of the plate in the xy directions. So that is done by, now come the coefficients. The gi's are these, okay, x11 phi 0 of x, chi 0 of y, these two. Then so this is 1, 2, 3, 1, 2, 3 plus x12 phi 0 x chi 1y plus x13 phi 0 x chi 2y plus x21 phi 1 of x chi 0y, and so on. Okay, finally x33 phi 2 of x chi 2 of y. These are your g's, g1, g2, g3, etc. Okay, then you compute your Vm and chi m by substituting this in there, and we found Vm chi m earlier. Okay, Vm and chi m we found earlier here. This is Vm, this is chi m we found earlier. Okay, then you start doing your del Vm by del x11 minus del chi m by del x11 omega square equal to 0. Then del Vm by del x12 minus omega square del chi m by del x12, etc. Start doing that, and then finally what? Finally you get your k x11 x12 minus omega square m x11 is equal to 0. Okay. Then you get an eigenvalue, generalized eigenvalue problem, find out your omega square. Okay. Then you multiply by rho h a fourth by d and take a square root, that is your square root of lambda, which is listed in the paper. Okay. Now, the simply supported, if all four sides are simply supported, then you have x of 0 is equal to x double dash of 0 is equal to x 1 is equal to x double dash 1 equal to 0, and the phi 0 is x minus 2x cube plus x fourth by integral 0 to 1 x minus 2x cube plus x fourth whole squared dx to the power half. If all four are clamped, all four sides are clamped, then you get x0 is equal to x dash 0 is equal to x1 is equal to x dash 1 equal to 0, and phi 0 x in this case is x square, okay, different from this, minus 2x cube plus x fourth by root of 0 to 1 x square minus 2x cube plus x fourth squared dx. Okay. And if one edge is clamped, the other is free. Okay, this is clamped and this is free, and this is clamped and this is free. Okay, then what do you have? So clamped, clamped, free, free. Then x0 is equal to x dash 0 is equal to x double dash 1 is equal to x triple dash 1 equal to 0. Then the phi 0 x is 6x square minus 4x cube plus x fourth divided by the square root of the integral of 6x square minus 4x cube plus x fourth squared dx. Okay. That means similarly psi y will be the same. Okay. The other direction psi y will be exactly the same with y. Psi y will be the same with y and so on. Okay. So then you can proceed and look at the square root lambda values. Okay. It's a very nice paper and work. So I will close the lecture here for today. We will continue in the next class. Thanks.